Hi guys, Harry here. Welcome to Scrap Science. So today we're finally going to get around to possibly the most requested video on my channel, which is, as you'll know from the title, generating nitric acid from, found some of this online, some potassium nitrate. The method that we're going to use to generate our nitric acid from our potassium nitrate is not going to be the standard mix it with concentrated sulfuric acid and then distill over nitric acid. In fact, we're going to be doing this by electrolysis, same way that we've made sulfuric acid in the past. The good thing about this method is that it doesn't require any kind of distillation in order to make dilute nitric acid, and it doesn't involve the generation of any nitrogen dioxide. So let's get into it. First thing you're going to need is obviously your potassium nitrate, and another good thing about this method is that potassium nitrate is the only chemical we'll need, the only consumable thing that we'll be using to generate our nitric acid, so we don't need sulfuric acid or anything like that. Next thing we need is a container, an inert container to do our reaction in. I'm just going to be using the bottom of a milk carton, and then we're also going to need some kind of porous membrane for our electrolysis to separate the products formed at the anode and the products formed at the cathode. The best and cheapest thing you can possibly get that I've found is a clay pot. These work really well, so we're going to be using one of those today. We're also going to need some electrodes. Today I'm just going to be using a copper cathode. You can choose any metal for this, but you know, copper's common and easy to use, so just go with that. And the anode, well, this is where oxidation is going to be taking place in electrolysis. You've only really got one or two choices for the anode in this kind of reaction, and that is graphite, as I've got here, or pure platinum. And I don't have pure platinum, so we're going to be using graphite. The final thing you'll need is some sort of power supply. What I've got is just a 12 volt power supply hooked up to my current controlled buck converter. You'll preferably want some kind of current control in the electrolysis, but I mean just a 12 volt power supply will do, I guess. And that should be it for the things that you need for this process. So let's get into it. I've measured out around about 100 grams worth of potassium nitrate, and all we're going to do is, into some warm water in your inert container, we're just going to try to dissolve all of that. And you just want to stir that around until almost all of it's dissolved. It doesn't matter if it doesn't all dissolve, because it'll have plenty of time to do that later. But what we should have now is a relatively concentrated solution of potassium nitrate in our inert container. And to actually set up for making nitric acid, we're going to get our membrane, that is our clay pot, and just stick that straight in to the container. And now we're pretty much ready to go. If we put the cathode into the outer chamber, this is where we've got our potassium nitrate, and then we've got our graphite anode within the inside of our membrane. All we need to do now is add some distilled water to the anode chamber, and then that is where we'll be generating our nitric acid. And now that that's all set up with some distilled water in there, we can go ahead and turn the power supply on and start making nitric acid. Go ahead and do that now. So I've turned the power supply on, and you can see not much is happening at this stage, and that's due to the fact that pure water, distilled water, is a really bad conductor of electricity. So we're not actually going to see much current flowing through the cell. Let's see. On our power supply we're getting about 90 milliamps, which really isn't much. But as soon as nitric acid production starts ramping up in the anode compartment, the conductivity of the solution here will increase drastically, and we'll start getting more current flowing through the cell. One other thing to mention before we go into the theory of how this generates nitric acid, you'll notice that the bottom of this clay pot used to have a hole in it, but I went ahead and plugged that with a bit of silicon sealant. So if you're going to be using the same kind of setup as me to generate your nitric acid, you need to remember to plug the hole in the bottom of the clay pot if it has one. Anyway, while we're letting that current build up as the concentration of acid in the anode chamber increases, I'll do my best to try to explain what's going on, why this is generating nitric acid. What we have to do is first start out by considering our solution of potassium nitrate in the cathode chamber here. What we've really got between our two electrodes is kind of an electric field of 7.5 volts. That's what we have it set at right now. So the charged ions, being potassium ions, positive, and nitrate ions, negative, they're going to be individually attracted to the positive anode and the negative cathode. So the potassium ions that are in the cathode chamber already are attracted to the cathode, and the negative nitrate ions are going to be attracted to the positive anode. Basically nothing is going to happen with the potassium ions in the cathode chamber because, well, they're already right next to the cathode, so they'll just stick around in the outside chamber. But with the nitrate ions, because we have that electric field pulling them across towards the anode, they'll actually be drawn through the semi-permeable membrane and into our distilled water over here. Of course, we also have to consider the actual reactions that are going to occur on each of the electrodes. On the cathode, we know reduction occurs, and the easiest reaction for the cathode to take part in is simply the reduction of water. Water is simply going to reduce to hydrogen gas and hydroxide ions. So really the only thing that we'll be adding to the cathode chamber is hydroxide ions, and we'll see that as the cathode chamber starts to become more basic. Right, we're going to be generating a mixture of potassium hydroxide and the potassium nitrate that's already in the chamber there. Now on the anode, we know oxidation takes place on the anode, and the only reaction, or the easiest reaction for the anode to take part in, is the oxidation of water. You might even be able to see, if I change the brightness a little bit, yep, water is being oxidized into oxygen gas and hydrogen ions, and you know hydrogen ions are what makes an acid an acid. Those hydrogen ions that are generated on the anode there are going to mix with the nitrate ions that are coming across through the membrane and give us our solution of relatively pure nitric acid. And that's about it. We know that potassium ions and nitrate ions are both pretty much electrochemically inert, so there's going to be no chemical changes to either of those ions. We know that all the nitrate ions that end up in here are going to stay as nitrate ions. They're not going to be oxidized by the anode, and the potassium ions aren't going to be reduced to potassium metal on the cathode because we're in the presence of water. So basically all we're going to be generating is potassium hydroxide in this chamber and nitric acid in that chamber, and the nitric acid is what we want. And really that's it. Nice and simple, generating nitric acid without any need for distillation or the generation of nitrogen dioxide gas. In fact, now that we've waited long enough, I've noticed that our current has risen all the way up to 630 milliamps. So hopefully we might actually be able to see, if we measure the pH of our anode chamber, we might be able to see the fact that it is actually turning acidic. And yeah, look at that, slightly acidic. That'd be our nitric acid. What's really strange is the fact that we haven't yet seen any hydrogen forming on the cathode there. Possibly we are reducing the nitrate ions into ammonium ions, which would not be ideal, but you know, that's okay. It's not going to affect the nitric acid that we generate over here. But you know, we'll wait and see where the hydrogen starts forming as we let the cell run for a bit longer. Now that the cell is running, there's not really much else we need to do to it other than leave it for maybe even a couple of days just to make sure that we get as many of those nitrate ions traversing through the membrane as possible. What I've done is just put it in this box that I use for the electrolysis projects that I do, simply to catch anything that spills out of the cell. Before I go, it's probably a good idea to mention that I have limited the current to about 1 amp just to protect the graphite anode, stop it from falling apart too quickly, because that tends to happen with graphite anodes. Alrighty, so I'm back. The cell has been running for about 3 hours now at about 1 amp. I don't know if you can read that down there, 1.01 amps it's at right now. So hopefully we've generated quite a bit of nitric acid in our anode compartment, you can see that the solution here, hello, you can see me in the reflection, the solution here has become quite a bit murkier simply due to all of the graphite particles that are falling off the anode there, because the anode will be disintegrating slowly. Hopefully that doesn't happen too quickly. The other thing I wanted to mention is the fact that the cathode has not generated any hydrogen gas at all, and I was quite worried about that fact just before. We should definitely be generating hydrogen gas in the electrolysis of water. That's one of the easiest reactions to do on a cathode surface. But I did some research just then and found that on a copper cathode, when there's nitrates present in high concentration like we have here, instead of reducing water to hydrogen gas, quite often the copper cathode will end up reducing nitrate ions to ammonia or ammonium ions. Don't quote me on that fact, because the only information I could find specifically about this electrolysis of potassium nitrate was like a paper from 1900 or something, which is a very long time ago. But anyway, it does explain why we're not generating hydrogen on the cathode. It's not ideal that we're generating ammonium ions in the cathode compartment, because that's using up nitrate ions that we should be using to generate nitric acid. But you know, there's not much I can change now. What I should have done from the start, if I had have been able to predict this, was put a second clay pot in there. I mean, this won't really fit in now. Should have got in a bigger container. But if I had a second container for which we could put the cathode into, right, then what would end up happening is the potassium ions would be attracted to the cathode compartment, which would then be in here, and we'd generate just potassium hydroxide inside that that clay pot there. The nitrate ions would exclusively go to the anode chamber and generate nitric acid, and we wouldn't see reduction of nitrate ions on the cathode, because the nitrate wouldn't be attracted over to the cathode chamber. So that would have been ideal, but sadly well, I've got this set up now and might as well leave it going. Anyway, I think I'll leave this going overnight, and I'll come back tomorrow and see what's happened to the cell and whether we have any more concentrated nitric acid. We are back the next morning. I've left it running overnight at about 1 amp, as I said before, and it seems to have gone pretty well. Nothing really looks like it's changed. See, we're still not generating hydrogen on the copper cathode, and it has turned black a little bit, which is a little bit odd, but that's alright. Still working. If we have a look at our graphite anode, we'll probably see that it has fallen apart quite a lot. Look at that, I'm surprised that was still conducting current, actually. So I'll have to make a new one of those, or maybe dip that further into the water. There we are, all I've done is just dipped it down a little further into the solution. You'll also notice that the water level inside the clay pot has decreased quite a bit, and that's probably due to osmotic pressure between the two. We've got a stronger solution of ions in this chamber than we do in this chamber, so water's being sucked into our cathode compartment. That's alright, it's not happening too fast, and we can always add a bit of distilled water to the anode compartment, so that's alright. Okie dokie, I am back the next day. It's pretty late in the afternoon, so it's now been over 48 hours since we started running this cell. I've put a second graphite rod in, which it's really fallen apart over the last 24 hours or so. And I think after more than 2 days, I think it's about time to stop the cell. So what I'm going to do is turn off the power supply, take out our what is hopefully a nitric acid solution, and whatever's in the cathode compartment. And there we have it. I've taken everything out of the cell. This is our hopefully nitric acid mixed in with a whole bunch of carbon particles, which will hopefully settle out pretty soon. And then this solution here is from our cathode compartment. It is very basic and smells very strongly of ammonia. So if anything, we've discovered that electrolysis of a nitrate salt on the cathode, with a copper cathode at least, will reduce the nitrate ion to ammonia. So I don't know if that information's useful, but we found that out either way. After more than 24 hours, I'm now ready to clean up and test our nitric acid. You can see that the graphite particles, the carbon particles from the electrodes, have settled down really quite nicely. The solution is actually quite clear, and you can see that layer of carbon sediment at the bottom, which we are going to try our best to leave behind in the beaker as we decant it off. And we're also going to filter our nitric acid solution into another beaker. So I'll go ahead and do that now. Now that that's done, we can see the filtration went surprisingly well. It's looking very, very clear and nice. Maybe slightly yellow, but that's all right. The next thing I'm going to do is just do a crude titration of our nitric acid, just to see if I can tell how concentrated it is. Right, so my crude titration tells us that the concentration of our acid is about 0.7 molar. The next thing we want to check is whether that concentration can actually dissolve copper metal. So I have some copper wire here, and I'm just going to drop that straight in. And we see pretty much no reaction, which is a little disappointing. Then again, 0.7 molar nitric acid probably just isn't enough to dissolve our copper metal. So what I'm going to try to do is heat up the acid on a hot plate and see if we can get a reaction going, because I'd quite like to dissolve some copper metal with this acid. I think that'd be a good achievement for the electrolytic method. So hopefully upon heating we are actually able to dissolve some of that metal. I think that's reacting. I mean, look at that. What I've had to do is kind of boil down the nitric acid to about 1/3 of its original volume in order to concentrate it, but I think we're now at the point where the copper is actually reacting with the acid. I might take that off the heat just so we can see what's going on. Hopefully it'll continue to react with that copper. You can see a slight blue tinge, which is good. I'll leave that to do its thing for a little bit. Yep, that is definitely reacting. You can see the copper there. So good, that's confirmation that we do actually have nitric acid. You can really see that blue tinge from this angle as well. After on and off heating for the last 20 minutes, you can see those little bits of copper wire are very nearly dissolved. Of course, we're being very wary of the nitrogen dioxide fumes coming out of this reaction. Alright, now that that's done, while that test of dissolving copper does indicate that we have made nitric acid, and making nitric acid is very good, that's a great achievement for this method of generating our acid. The concentration of our acid is really pretty woeful. For starters, I initially used 20 milliliters of our nitric acid solution in order to try to dissolve the copper, and what I ended up having to do was boil that down all the way to about 5 milliliters before any reaction took place, which we need a concentration of a bit under 2 molar, I believe, in order to react with copper at high temperatures visibly. So my estimate of 0.7 molar for this solution wasn't too far off. Maybe it's 0.5 molar or something like that, maybe even a little less. In fact, by the end of the heating, you can see that we had boiled down our acid to less than 1 milliliter worth of volume. So now it's really definitely not very concentrated, the stuff that we've made. Now, while low concentration nitric acid is pretty useful, I mean, it's really good for cleaning stuff and making nitrate salts, despite all that, it's the concentrated nitric acid stuff, or at least more concentrated than 0.5 molar, that is the really useful stuff that can dissolve copper, can dissolve silver, stuff like that. So while this method works in generating very low concentration nitric acid, which might be useful to you, and if that's the case, then maybe you'll like this method. If you need concentrated stuff, this really isn't the method for generating it, simply because you have to boil it down in order to get the concentrated stuff. And if you're going to do that, then you may as well just make it by distilling your potassium nitrate with sulfuric acid. And I don't know, maybe you can't get sulfuric acid easily, or maybe it's too expensive for you and you like this method because it doesn't involve the use of sulfuric acid. But to me, just the really low concentration of nitric acid that we get out of it, and the fact that we have about a 10% yield from the amount of nitrate that we put in here initially, it's really not good enough for making nitric acid at all. There might be ways to improve the method. I don't know, maybe, like I said before, adding a second membrane in there to stop the reduction of nitrate back into ammonia. That might increase our yield drastically. I don't know. Maybe I'll try it at some point in the future if there's enough interest. But as it is, this method isn't good enough for practical use, and there'll need to be some improvements made to the process if we want it to be viable. But maybe that's for a future video. Or maybe not. We'll see. And anyway, on that note, that's it. See you later.